Yes, sir.
So am I audible?
Yeah, yeah.
Okay. So in last lecture, you asked me to review some non-Hermitian optics and Hermitian optics, right?
Yes, sir.
Yeah. So I found one good review paper. I can share you with you. Review paper is the topic is non-Hermitian optics and photonics from classical to quantum. Okay. Uh, Author is Lan Yang, and this is published in Advances in Optics and Photonics, or volume 15, number 2, published in June 2023. Okay.
Okay.
So this is the paper. This is around 100-page paper only. Very long paper, but uh, that much long paper. There are some introduction part, then fundamental description of non-Hermitian physics. In this section, they explain something Hermitian operators, non-Hermitian operators, then PT symmetry. Okay, so all these three conditions are very important to understand what is non-Hermitian system. Okay. Then the implementation of non-Hermitian physics in wave optics. In that one, they explain principle of non-Hermitian photonics and wave propagation in complex optical media, like that. So if you read till third one, you will understand. After that, they start discussion on exceptional point physics type, some advanced, which is used, which is the consequence of this non-Hermitian physics only. Okay.
Okay.
So the basic idea is you heard about in the uh, thermodynamics that some systems are open, some systems are closed, right?
Yes.
So what are these open system, and what is the closed system?
Yeah, when the system is able to interact with the environment, then it is a open system,
Okay.
as I can recall. And whenever, just give me 1 second.
Okay. Okay.
Ah, ah. And when the system is closed, that is, in that case, it is not interacting with the ambient boundary or ambient environment.
Okay. So these two type of system you read. Okay. So in this advanced term, you can say that the whatever the closed system is, these are all Hermitian system. Okay, and whatever the open system is,
Okay, sir.
they are considered as a non-Hermitian system. And if
Okay.
you saw in the point of view of quantum mechanics, so in quantum mechanics, the uh, Hermitian operator are there. Okay, so if we apply to the Hermitian system, then the Hermitian operator have the value of eigenvalue of real. Okay, so these real values can be implemented in the real world, but if you solve with with non-Hermitian system, then the eigenvalue comes the complex or imaginary. Okay, so these cannot be realized in the real system, but on the with some constant, like if you have some pt symmetry in non-Hermitian system, then you can realize this non-Hermitian or open system in the real world, because open system is only the in the real world exist. So you have to think about this one. While we are explaining all the physics, we consider all the system as a closed system, right? So we consider it as a Hermitian system. So like Hermitian operator are there. So Hermitian operator have these you know the Hermitian condition in the matrix. If some matrix has
A dagger is equal to
is
A,
equal to
something
A,
like
so
that.
this is the Hermitian matrix. So if this type of operator something, then you can say Hermitian system, Hermitian operator. Okay.
Okay.
So this is the one of the very basic definition of Hermitian and non-Hermitian system. And this pt symmetry means this is time reversal symmetry, and parity symmetry should be also there to be non-Hermitian in non-Hermitian system to solve these non-Hermitian system.
Sir, please
Okay.
excuse me. Can you just go to the previous page? Yeah, sir, at the end of this page, you showed the difference. This real and PT symmetry system, this thing I couldn't understand. Can you please just explain it once again?
Okay. So I am saying that the Hermitian system, if you have Hermitian system, okay, in quantum mechanics, if you have some Hermitian operator, then the eigenvalue of that Hermitian operator is real.
Okay,
Okay, so this is one advantage of this Hermitian system, because in the real world only these system can exist which have some eigenvalue of the real. And the complex if you have some complex eigenvalue, so
okay,
these operators which has non-Hermitian, they gives us to complex eigenvalue or imaginary eigenvalue.
okay,
Okay, so one difference between Hermitian and non-Hermitian system is this one, on the basis
hmm,
of eigenvalue. Okay, and I am saying that uh, this non-Hermitian system can be solved if they have some type of pt symmetry,
okay,
then they can solve as a Hermitian system in some uh, extent, till some extent. So and more on, if you want to read, then you can read this paper. This gives very good review paper on this.
Sir, can you just copy paste the DOI of this paper if it is available with you in the chat box,
DOI.
or any link, anything will work.
Uh, One second, I have to search on the Google, then I will share.
Okay, okay, fine, sir. I'm just searching it. Okay, no issue. I'll just search it. Okay, so thank you.
Okay, so this is from last week you asked about this one, and in this week mostly talk about strong coupling, Ravi splitting, and some difference between weak coupling and strong coupling. So all you understand all these things which is discussed in the lectures.
Uh, no, actually, I have some like my understanding is not clear because in first few classes, like when he was talking about those uh, Rabi frequency,
Sorry.
Rabi frequency. When sir was talking about that those Rabi frequency, na, so actually I was just unable to get to the point like how these things are helpful for like implementation in real systems. So
So Ravi frequency or Ravi splitting.
Rabi frequency splitting, I don't think like there was any term used as Rabi splitting.
Okay. Because mostly when we talk about strong coupling, then we talk about splitting of uh, Ravi splitting. We talk about mostly.
Okay, okay.
Okay, Ravi frequency is also is the frequency at which the probability amplitude of two atomic energy, like there are two atomic energy level are there. Okay,
Hmm. Hmm.
then uh, these two levels, uh, then probability amplitude of two atomic energy levels fluctuates in an oscillating electromagnetic field, and we apply some electromagnetic field to these two levels, then it fluctuates between these two levels, right? So I think
Hmm.
that is only Ravi splitting is the Ravi frequency, I think, because these two levels are here, and the probability of amplitude whatever is here and here is something is Ravi frequency, I think.
Um, okay.
Okay, okay, okay. See, mm, mostly like strong coupling and weak coupling things. One second.
Uh,
So if you have one oscillator, like this is we can have like Fabry Perot, or you can have some mechanical oscillator, you know, right?
hmm.
Two spring mass, and it is connected to some spring, right? So what happens if you couple two oscillator, they can have either symmetric modes or anti-symmetric mode, right?
Yes.
Yeah. So like let's say this is omega, and sorry, one is omega, and you can say this one. So if you have two frequency of these two have two resonators have two oscillations, okay, then when this is crossing, at crossing they split into one and two things. So this splitting is comes under strong coupling. So in a strong coupling, there is one condition between, let's say these two oscillator have some coupling strength, capital omega, okay, and some gamma, some loss in between this oscillator have some initial loss, inherent loss, that is called gamma. And if exchange of energy in these two oscillators is greater than the sum of the loss between these two, then only this condition can happen. So these two are known as upper polariton or lower polariton. So the modes which have lower energy is known as lower polariton, or this is high polariton. Or you can say like two hydrogen atom comes together, then when they make H2, then they have two energy level splitted, right, when they comes together. So this is called some anti crossing, and this is symmetric of the bond. So these two levels, if you applied some energy, electric energy, energy difference between these two energy levels, then it oscillate between these two levels. I think that is only called Rabi frequency, at which they start to couple uh, strongly. At which frequency? Let's say uh, like this is one oscillator, okay. Let's say about optical oscillator. So optical oscillator you can consider as a Fabry Perot or any type of optical resonator. Then let's say its frequency is omega 0, its oscillating frequency is omega 0, and it have two type of radiation. One is non-radiative radiation, one is radiative loss. Two type of loss there will be. So you can write gamma is equal to gamma nr plus gamma r, okay, for this oscillator. And some photon comes here of the same frequency, that is called omega 0, okay, and its loss is, let's say, gamma m, that is we consider material loss, okay. And the coupling between these two things, let's say capital omega, okay. So now if we plot between this omega and omega plus gamma nr, which is sorry, this is at gamma m and here is gamma r only, okay. So what will happens, see, gamma r is equal to gamma nr plus into plus gamma r, right.
Yes.
So and gamma nr will be some constant value at
Okay.
y-axis. Then there are some reason, let's say this is the point where this is omega point. Omega is such that it has value omega m, right.
Okay.
So this is gamma r, which is equal to gamma radiative and gamma nr. Okay, so and actually some derivation is in between there. So see, gamma m we consider as a material loss. Material loss is inherent, right?
Hmm.
This is the material loss, and the photon is coming which has two type of radiation, that is non-radiative and radiative. So if gamma m will be gamma m plus gamma n r equal to gamma r, if this condition will satisfy, so this is the equation of this line, right?
Okay.
So this line considered as a strong coupling line. Strong, not strong coupling, it is called critical strong coupling, because this is exact equal to gamma r. Okay, and
Hmm.
if gamma r will be greater than gamma m plus gamma nr, so in which region we will come?
Gamma, gamma, gamma m plus gamma. I think we'll get in the left hand side of the straight line.
This one, right?
Yeah.
This region. Okay,
Hmm.
and in this region what will happen? So this region is known as B coupling, because at this point this is the omega point,
Okay.
and this point is something called, at this axis you can say omega plus gamma nr at this point. So if omega, so there are three types of condition you can have. One is gamma m, gamma r minus gamma nr, it should be omega to the power omega square, and one condition is this one. So this is a strong coupling and this is for weak coupling. So this condition comes in this region, and this, if it is in this region, that is it is called strong coupling, and at this line this is critical strong coupling. So what is the difference all these three? I can plot, like if you have some omega and we plot it at absorbance, like, okay, so if you have maximum absorbance will be 1, right?
Hmm.
So if you have this type of, so these two splitting is means this is strong coupling region, and if absorbance reached at 1, that is on which I plot this line, that means you are at this line. But if you have splitting but not exact absorbance of 1, or this max a max is less than 1, still you are have in strong coupling region, but you have something in this region. Okay, so this is called perfect absorber. Whatever energy will go in this condition will be absorbed by the system. No transmission, no reflection. Okay.
Sir, can you please explain, like, here the absorption coefficient is
Mm-hmm.
less than 1. Okay.
Uh-huh.
So how this is working as a perfect absorber?
This is not perfect absorber, this is less than 1. Only this red
Uh,
condition when
okay.
it
Okay.
reached 1. So this is
Okay.
perfect absorber. So perfect absorber you can reach at this line only.
Okay. Is it something
Otherwise
also
you are
create
in
the
strong coupling region but not at critical uh, strong coupling region. This is your critical strong coupling.
Okay, okay. Sir, is this
Mm.
plot is something like the phase diagram of the material of the of
Phase.
some system or something like that? Because since there are three regions, as I can see,
Mm.
one is strong coupling region, another is the weak coupling
B
region,
coupling region. This is
and
B coupling region.
okay. And sir, the what is the importance of the part which is above the straight line? But
Uh, this,
in the
this one.
no, that left hand side of the
Yeah, this one.
yeah, yeah.
This will not you will get because this is the reason at which mm, mm, this is not any this is also a strong coupling region, I think. mm, at this point I have gamma and r. So if you have at this point, so you have gamma m is equal to gamma r plus gamma. And if you have gamma m is greater than gamma r plus gamma nr, should do this uh, derivation, I think. Then mostly people talk about this region and this region. This region is weak coupling, and this line is also weak critical coupling.
Okay, sir, fine. Okay.
Mm. Because if you go in this region, then you will not see the splitting. You just absorbance will be like that. Okay,
Okay.
and if you have absorbance 1 in this region, then this is also a you can say perfect absorber, but without strong coupling.
Okay.
Uh, and if you consider that the coupling omega is coupling between cavity and the matter, like, okay, so if you have this omega equal to 0, then you will have only the relation this gamma nr, this will be gamma r and this will be gamma m. Okay, so above this line you will see critical coupling, and below is also critical coupling. Okay, I think what you are asking, this region will be also the strong coupling region. In strong coupling region, you will get this type of curve, not this red one type of curve.
Okay, sir.
Hmm. Which I can understand from this curve, because in this region, if you have this when gamma equal to 0, then you have this type of phase diagram. Okay, if you consider omega some non-zero, then you will have this curve. So in this curve, you are in this region or in this region.
Okay.
In both case you will be like absorbance. If this is 1, then like this only, because this is weak coupling, not a strong coupling, so you will not get this splitting, but you will get the absorbance less than 1. Okay, but at this line, if you will plot, then you will get without splitting absorbance is equal to 1. So what is the importance of this splitting? See, in this region we talk about Purcell factor. Okay, we calculate the Purcell factor, enhancement of Purcell factor, whatever it is. So the Purcell factor is something which is directly proportional to Q factor, inversely proportional to mode volume. Okay, and lambda to the power q, something like that. This is not exact equal to, but maybe some term will come. So if q factor will increase, then Purcell factor will increase, right?
Yes, sir.
And if mode volume will be lesser, then also the Purcell factor will increase. So Purcell factor is the quantity when we characterize the weak coupling region only. Okay, in
Okay.
strong coupling region we talk about the Rabi splitting, this splitting energy, because in this state, this is known as, like, if you have matter and one exciton. Okay,
Hmm.
so on the basis of that, it is called exciton polariton. You heard name?
Yeah, actually, I don't have that much concept on this exciton polariton things. So,
Okay, so exciton polariton, and one other word, you can say plasmon polariton, and third one is you can say phonon polariton. So this polariton word is common. So polariton word is comes when you have a strong coupling region. Okay.
okay.
So what is polariton? Polariton is not a matter state, not a electromagnetic state. This is half quanta and half matter. Okay. So see, this matter has some mass, right?
Hmm.
And quanta has some energy. Like if you have quanta, you cannot access matter property, right? And if you have some matter, you cannot access the this photon property. But in polariton you have half quanta and half matter state, so you can access both property with this polariton things. And this polariton can exist only in strong coupling. So what we need for polariton? One matter plus anything, either exciton or plasmon or phonon. Okay, if phonon couples with matter, strongly coupled, then you said uh, phonon polariton. If exciton couples with the matter, then you called it as exciton polariton. Like, see, we have one cavity. Okay, cavity resonance we can tune. For example, with some parameter, you can say this is lambda, or at this you can say some property like height of some uh, resonator. Okay, like you have some disk resonator, area of disk resonator, and h is the, so if you increase the h, the for cavity resonance will tune, right?
Okay.
So you can consider the mode, one mode like that. Okay, and if you
Okay.
have some exciton, maybe some gain material, you can say gain material like dye or some 2D material or gallium phosphide or something, they are the gain material which you can excite, they give the PL. Okay, in PL there will be some photon, right? Like if you have photon, so photon energy will be constant, whatever the material, gain material will be constant photon energy. Okay, so that will be constant. So when the cavity resonance and exciton resonance meets with the condition of E resonance of cavity is equal to E resonance of that exciton, and one more condition, this gamma cavity is equal to gamma exciton. These two conditions when meets at this point, then this will be like something, will go like that, and this one. So this splitting will happens at this point. This is
Okay.
only the condition for strong coupling, and this Rabi splitting, maximum Rabi splitting will be at this point only. Okay,
Yes.
so this is the concept of strong coupling. This is the main condition for strong coupling. These two things, or many people start with this coupled mode theory to calculate this splitting.
Sir, I just have one question. Like, if you can you please go to the previous page? Uh, yeah, sir. Here, as I can see, like, the damping factor is coming everywhere. Like,
Yes.
is there any relation between the damping factor and the quality factor of this kind of absorption curve?
Yes. See, this absorbance curve is mainly like uh, this gamma R we talking about, na?
Hmm.
So this gamma R is inversely proportional to 1 upon QR.
Okay.
Okay, and gamma M is directly inversely proportional to QM. Okay, and the resultant Q factor, you can say this relation QR plus QM, or you can say Q int, whatever intrinsic Q factor, intrinsic loss of the material, which uh, whatever the intrinsic radiation, intrinsic loss of the material contribute to the intrinsic quality factor. It is called intrinsic quality factor of material. Okay, in some cases this is constant, like you have this uh, n dash plus ik, so this is absorbance things, right? So this
Yes.
absorbance will come in this q factor only. But whatever we are making this cavity things, so whatever the radiation loss will be there, that is called radiation quality factor. So mostly we talk about radiation quality factor when we make the nanostructures. Okay, because these are inherent and you cannot avoid these things. So this factor will be always there. Only we can tune this factor in
Okay.
the nanostructures. Okay. should I go to the tutorial?
Yes, sir. Yes.
Okay. So tutorial question number is given this Ravi oscillation exchange the population density in a quantum system due to strong incident electric field. So what will be 1 level, 2 level, 3 level or 4 level? What will be the answer? So Rabi oscillation exchange the population density in a which
Okay, it's a
system?
two-level system,
Two level
obviously.
system which I talk about. Okay.
Hmm.
Because this is E1 and E2. See, you are here saying this strong incident electric field.
Hmm.
Okay, so because when we pump any material such that this much strong electric field which can see strong coupling when it will happen. I said initially statement this is the exchange energy between cavity and the electric field, right?
Okay.
Because strong coupling we are talking about half matter and half light state. Okay, so in which one is light and one is matter. So the gamma is the exchange energy between matter and electric field. Okay, so if you have that cavity, the radiation loss is very less and the material loss is also very less. Okay, less in compared to this exchange energy, because energy between cavity and light exchange rate is very high, so that it cannot radiate, and gamma m is in compared to this one, then only this Rabi splitting or Rabi oscillation can happen. Understand what is the statement?
No, sir. Can you please repeat that one?
Okay, see, you and your friend. Okay, you are the
Hmm.
like light and your friend is matter. Okay, so some loss, you also have some loss. Okay, and your friend has some loss type thing, like
Okay.
I can say, like if we talk about mind, so भूलने का एक होता है ना, you can
Hmm.
also forget, he can also forget, but different rate, right?
Hmm.
but तुम दोनों के भूलने का जो रेट अगर हम ऐड कर दें,
Hmm.
अगर वो तुम दोनों के बीच में जो एक्सचेंज करने का जो रेट है वो ज़्यादा हो
Hmm.
जाए.
Okay. Okay. In that case, it
This
will help us to remember everything.
yes, so that is that is called Rabi oscillation.
Okay.
One is matter, one is cavity. Cavity and matter has some exchange rate, that is called this capital omega. And gamma R and gamma m is the cavity loss and material loss. The cavity material loss and gamma are the radiative loss of this cavity. Okay,
Okay.
or whatever energy we are pumping it. That is called the incident electric field. So if the exchange rate of higher than the loss of these two, sum of loss of these two, then only this Rabi oscillation can happen.
Okay, sir.
So this is happens in two level system. Okay. Then question two is observation of Rabi oscillation is signature of strong coupling only. Okay.
Okay.
Actually, this Rabi splitting which we are um, repeatedly saying, that is only the Rabi oscillation. Okay, so that is okay. Observation of Rabi oscillation is the signature of strong coupling. This is second question. I just this will be strong coupling, right?
Yes, sir.
Similarly, question 3. In question 3, there is given this is 1, this is 0, and this is C2T mod square. Okay, probability of atom in state oscillator with time. So this is time omega t upon 2 pi. Okay, so this is one curve is like that, another curve is like that, and one curve is like that. This is C, this is B, this is A. Okay, the question is
হ্যাঁ সুমনদা বলো। আরে আমি ক্লাসটা করছি স্ট্যাটার সঙ্গে। হুম, হুম।
so which of the following curve represents the strong coupling? Strong coupling, which curve?
Sir, I
A,
think
B or C?
A will be a strong coupling, and some sort of B will also some kind of coupling is occurring there.
Yeah. See, this is the strong coupling when this one is happening. Okay. So this is
Mhm.
critical strong coupling, exact strong coupling, and this
Mhm.
is also strong coupling region. Okay, because this is oscillating, but it is damped with the time because this exchange of the energy is has some damping rate. Okay.
Okay.
So this A and V is the strong coupling. Similarly, for let's omega r is the Rabi oscillation frequency. Okay. Okay, now I got it. Its terminology. So omega r be the Rabi oscillation frequency and gamma I is the damping rate.
Mhm.
Okay, this is Ravi splitting. So which why I am talking about this omega. This is the omega r only. What
Okay.
is the splitting? That is called Ravi frequency. Got it?
Okay.
Whatever I am talking about this splitting, na.
Mm-hmm.
So this is omega r only in my term, and they are
Okay.
called it Rabi oscillation frequency. I am called it Ravi splitting. This is also the energy term, right?
Mm-hmm.
So omega r and gamma I is the damping rate. So for एक जो A curve है, what is the relation between omega r and gamma I?
For curve A. Okay. For curve A. I think both of them are equal, like omega equal to omega r, or something like that.
No. See, damping will be zero. Then only you can reach
Oh,
that.
yeah, yeah, yeah. Sorry, sorry, I made a mistake.
Okay.
Yes.
So
Yeah.
gamma I upon omega you can say zero.
Yes, sir.
So this is the answer.
Um,
Uh, Similarly, question number 5.
Sir, if I ask you like, actually we are having similar type of question in our assignment also this time.
Okay.
Okay, so like along with this question, he has associated some Q factor type of thing here. Okay, so that's why I'm just asking you like, if I suppose for this question number four, okay,
Okay.
when that omega I, sorry, gamma I by omega is equal to zero. So
Mhm.
in that case, like how the quality factor will get affected
So this
in this?
gamma I equal to 0, then it means qi will be infinite,
Okay.
because see, what is gamma? Gamma is damping rate. Okay, so this
Hmm.
is termed as a time, tau. And what is q factor? The basic definition of q factor is uh,
Delta omega by omega or something
uh,
like that.
how long any cavity, how long this energy can sustain in that cavity.
Okay.
Okay, if it is and gamma is the loss rate. Okay, how fast this gamma is, energy is leaking from the cavity, that is gamma. Okay,
Oh,
so this is just opposite. So the q factor formula is 1 upon tau. And tau,
okay.
how you calculate the tau? You calculate this tau with this fwhm, right?
Okay.
And this fwhm is known as gamma.
Okay.
This term only is known as gamma. So this is only gamma, I think. So you have, if you have gamma is equal to 1 into 10 to power minus 3, then q factor will be 1 upon 1 into 10 to power minus 3 is equal to 10 to power 3. This is the
Okay.
only relation between gamma and q.
Okay, sir.
But it only depends what type of your gamma, then that type of q factor only you can calculate. If you have radiative gamma, then you can calculate radiative q factor. If you have
Okay.
intrinsic gamma, then you can calculate intrinsic q factor. Okay, and the total q factor is equal to 1 upon q radiative plus 1 upon q intrinsic. So in intrinsic, all the material loss and whatever is there, whatever type of loss you can uh, define, uh, the q factor will be just like this formula. Whatever, this is one type of loss, this is another type of loss, this is q factor corresponding another type of loss. So
Okay.
q factor, q total will be like that formula. Okay.
Okay, sir.
Hmm. So fifth question is, let's gamma r with the Rabi oscillation frequency. Okay, gamma r is Rabi oscillating frequency, and gamma I with the damping rate.
Okay.
So choose the correct option relating gamma I gamma r for curve B. So curve B has some damping rate, right? If you see here,
Okay.
some
Uh,
damping rate. Okay,
so
so
in that case, it would be like in between zero
but it
and
is
one.
in strong coupling region. Okay, so
Hmm.
in strong coupling region, always gamma I will be less than omega r.
Hmm.
Okay, this is the strong coupling region, and if you divide by gamma r, so gamma I will be omega r will be less than 1. Okay, see, I told you gamma m plus gamma n, gamma r. Okay, these two are only gamma I, then this should be this omega r, it will be strong coupling, right? What I told you,
Yes.
this
Hmm.
rate of change of exchange energy between cavity and the light should be greater than loss of individual.
Yes.
So question number 6, In curve C, we do not observe any oscillation in probability of finding carriers in excited state. This is because for C के लिए कौन सा रिलेशन रहेगा?
I
डैम्पिंग
think
ज़्यादा है, सो
omega
गामा
equal
आई
to
विल बी
gamma.
greater than omega r. Okay,
Okay.
but there is no answer such like that. So there are mostly is giving like in this term. So if you inverse this 1 upon gamma I, this will be inverted, right?
Yes.
So this will be the answer. So question number 6. No, 6 was this one, right? Oh. So question number 7. Consider a resonant cavity. So sir also talked about some fabrication of nano resonators.
Yes. Yes.
So you understand all the fabrication process?
Yeah, a bit like
Uh,
whatever he has taught, I have gone through that, but I don't
okay.
feel
So
like if I
if
am
you have some doubt in fabrication, I can told you because I mostly done in fabrication in my PhD.
okay.
So consider a resonant cavity. Cavity volume is V, right? Okay, and
Yes.
quality factor is Q, and quality factor is Q at particular wavelength, some wavelength at lambda. Okay, has a Purcell factor of F, and this is volume, and this is Q factor, and this is wavelength for one cavity. If volume of the cavity has been doubled, let's say V2 is equal to 2V, and quality factor is also doubled, so Q2 is 2Q, then what will be the effect of Purcell factor? I will say this is all B1, Q1, F1
Yeah, it remains constant.
at the same lambda. Okay, so F2 will be F1. Why? Q upon V, lambda is constant. Okay, so this
Hmm.
F1 by F2 will be Q1 बटे B1 multiply by V2 बटे Q2. Okay,
Yes.
so this will be Q1 बटे B1 multiply by 2B1 upon 2Q1. So it will be F1 equal to F2. So question number 8 is, in an optical lithography system the resolution can be improved. Good question. Optical lithography system, resolution, how you can improve the resolution? I told, I think in first or second lecture, one very, when it comes the optical term, right?
Hmm.
So very many things are limited by diffraction limit. Okay, so this diffraction limit directly proportional to lambda by 2. Okay, And if you want to less resolution, then lambda should be less, right?
Yes, sir.
And this lambda is for what? Source of UV light, right? From which we expose the structure to make. You know the optical lithography, right?
Yeah, I just gone through the lectures.
And second term is numerical aperture, because resolution will be higher if numerical aperture will be higher. Okay.
Okay.
So for resolution, so sorry, mm, I put it resolution will be higher. रेजोल्यूशन मीन्स अपोजिट है ना, लेंथ जितना कम लेंथ हम आइडेंटिफाई कर सकते हैं, दैट इज रेजोल्यूशन, राइट? सो
Yes.
लैम्डा विल बी लेसर, दिस दिस लेंथ विल
Whenever
बी
if
लेस,
we
देन
increase the
रेजोल्यूशन विल बी हायर.
resolution will be higher.
हाँ, okay. And the numerical aperture, because numerical aperture is something like if it is the objective, right, then how much angle it can collect, so that will depend on numerical aperture. Okay, so if this is very, so for resolution you have to collect the light from the wider angle or smaller angle, sorry. So numerical aperture is one constant in the optical lithography. So these two the main thing to increase the resolution of optical lithography. Question number 8, 9. If you read about nano fabrication, okay, so which lithography you used for the nano fabrication?
Lithography techniques.
हाँ, okay. So the question is, which of the following statement is true in terms of nano fabrication? Okay, so first statement is lithography system is used to pattern structure on the substrate or wafer. Okay, so they called lithography. This is okay, right? See, lithography means, litho means, what is litho, what is graphy? Litho means some type of stone, right?
Yes, sir.
And graphy means whatever design you are doing. So if you are doing design on your stone, that process is called lithography. Okay, like what it is called in English, मूर्ति जो लोग बनाते हैं, okay, so they also did lithography. Okay, writing on the stone is called lithography. But if you have some wafer or some nano scale level writing, if you want some structure in nano level, then you should go this photolithography or EVM lithography, but they are also called lithography term. Okay, so see, if you have some structure like 2 micron or greater, then you can go with photolithography. If you have some structure less than 2 micron, if you want precisely, then you should go this e-beam lithography. So the difference between these two are resolution. Okay, in
Yes, sir.
photolithography and e-beam lithography. And also photolithography and e-beam lithography, here source is light, that is UV light. According to your resolution you can choose the wavelength. And e-beam lithography, there is electron beam is exposing the whatever you have resistor or something. So but e-beam has higher resolution, because if you calculate the wavelength of e-beam, it comes around 0.1 nanometer something. Okay,
Okay.
that's why the e-beam lithography has the higher resolution than photolithography. This is just for information. And the another statement is ellipsometry is used to pattern structure on substrate wafer. Ellipsometry, you know.
No, sir, I don't remember.
Okay, see, uh, in fabrication, what you need, first you need deposition. Okay, whatever you have the material, like you have silicon structure or you have silicon nitride structure, gallium phosphide, gallium indium phosphide, whatever you have, you need to deposit that material. Okay,
Okay.
very first, like this is your wafer, so
Mm.
you need some material, whatever you have to pattern. Okay, on top of this, so this is known as technique deposition. And if you go to the deposition technique, there are lots of deposition technique like CBD, PVD, sputter, spin coating. Okay, CBD is chemical vapor deposition, PVD is physical vapor deposition, sputtering. uh, like if you go CBD, so chemical vapor deposition, you have one substrate, you have substrate here. Like this is something like this is the one type of CBD I am telling about. So you
Mm.
have some material here, and you are heating this, and the vapor is going, and then it chemically reaction, and if you have some substrate on this one, it deposited on this one, and some or gases are wasted from the tube. So this is some type of analogy the in CVD is used. Sputtering, some material is there, we heat the we heat this material, and our substrate is here. Okay, so plasma forms. In presence of plasma, this material heats, and the atom goes to this and sit on this substrate. So this is technique called sputtering.
Okay.
Okay, so if these are I am just touching the words, what the words we are using in fabrication. So
Mm.
CBD, PVD, sputtering, spin coating, all these are types of deposition technique. Okay, next you have to pattern these things, right? So this is your material, below there is some substrate, and then you have to pattern this, right? Maybe some this type of structure you have to pattern. So for that one, after deposition, you need lithography.
Okay, and under this lithography, I think that masking and etching, everything will come, right?
Yes, yes, yeah, and under
Okay.
this lithography it will come. And like these are some fabrication term, but you also need some uh, what it is called, measurement or monitoring, what how much deposition thickness, all these things, right? Like how much thick you have to deposit this film, This is you had to know, and you should know. Otherwise, you cannot pattern any height of material for any resonance wavelength.
Okay.
So for measurement of this thickness, also you want to measure the refractive index of this material before doing patterning, because in simulation you have to you had calculated with some refractive index and with some parameters, structural parameters. So for this measurement, there are, for thickness measurement, let's say, there are techniques: DAC, profilometer. This is one term, DAC, profilometer. Other is ellipsometry, and third thing, optical profilometer is also there. Optical profilometer works on interference basis, like one reference plane is there, and this is your plane to measure. Then if light is coming and reflecting back here, and also the light is coming on this substrate, and whatever fringes will forms, the difference between these two surface morphology, then you can calculate the roughness and the thickness using
Okay.
this one. Okay, one reference plane is used for that one. And that type profilometer is like something, this, some type of this tip is there, and this is your material, and let's say you have just make a step, then it go from here to here, and it will measure this thickness. So this is something dactyl profilometer. AFM is also there, atomic force microscopy. So in this one you can calculate the roughness, phase, many things you can calculate from AFM. So all these techniques are characterization techniques. All these are some fabrication techniques. Okay.
Okay.
So in this one, there, in ellipsometry, the light comes on the substrate, and then they check the phi, and psi, these two parameters. This psi related to some p polarized light, phi related to some s polarized light, and then some fitting is there, and some fitting parameters they already have the data. So from that they calculate whatever your refractive index as well as the thickness of your film. So mostly ellipsometry is done for the substrate which are transparent or light can transmit through. You
Okay.
cannot measure the thickness and refractive index for the gold from the ellipsometry, because from the gold, the light reflected back from the surface only. It did not go inside the um, gold, right?
Okay.
So ellipsometry cannot be used for such materials. So ellipsometry mainly refractive index as well as uh, thickness you can measure, these two parameters from ellipsometry. From dactyl profilometer you can measure the roughness of your surface as well as the thickness of your surface. You can say surface morphology. All the technique is used for the surface morphology, calculating surface morphology. Okay.
Okay.
So the second statement, ellipsometry is used to pattern structure on substrate. This is wrong, right? Because ellipsometry is for the thickness measurement and refractive index measurement,
Okay.
and lithography system is used to measure the thickness of the film. That is also wrong. And the D statement is ellipsometry is used to measure the thickness and optical constant of the film. This is true. Okay. So this
Hmm.
ellipsometry you can use refractive index. So refractive index is the optical constant. Okay. Because there are many types of models in the ellipsometry software. When it measured phi and psi from your sample, After that, there are many models. Cauchy model is the famous. You should know, right? Cauchy model, you know?
I can't recall at this
Okay.
moment.
So in this one, refractive index is something a by lambda plus b by lambda square plus c by lambda cube, like that. So at some wavelength, this a and b c are the optical constant. These are known as optical constant for
Okay, okay. Is
Cauchy
this
parameter.
the theories of diffraction or something like that? Uh,
Actually,
that
I
we,
also did not remember the all the.
I think for Cauchy model, like I think the second up to second order that we used to take or something like
Yes,
that.
yes, yes, something like that. So
Yeah.
these are some optical constant you can measure from this ellipsometry,
Okay.
and by calculating this ABC, you can calculate this refractive index and for the particular lambda.
Yeah, yeah, yeah. That is for the diffraction. Yeah. Okay.
Yeah. Okay. Next, question 10 and 11. So a Fabry-Perot resonant cavity. So you have Fabry-Perot. FBI will write.
Hmm.
Fabry-Perot cavity is generally made of two mirrors. Okay, these are two mirrors. Reflectivity is R1 and R2. Okay, and R1 is equal to R2 is equal to R. This is equal refract. So the figure below depicts the transmission spectrum of three Fabry-Perot cavity A, B, and C, whose mirror refractivity are given RA, RB, and RC. So and second one is okay. So this is R1. Okay, this is RA, this is RV, and this is RC. Okay, R1 is equal to R2 is equal to R. So first question is, what can be deduced about the refractivities of cavity A, B, and C from transmission spectrum?
Okay. I think RC will be maximum of them, and
If R will increase, what about the Q factor?
the Q factor will decrease if R is increased.
No.
Sorry. Yeah, sorry. Just give me 1 second. RC is the red one. Okay. Then Q factor will increase with the RC.
No, I am just asking in general, if
Hmm.
our reflectivity increase, what will be the Q factor effect? Q factor will also increase, okay?
Hmm.
Because reflectivity will be less means loss is there. That's
Yes.
why this reflectivity is less, right?
Yes, sir.
Absorption or something. So then Q factor will decrease if losses will be higher. Okay.
Hmm.
So according to that formula, how can you relate RB, RA, RB, RC? So RC will be higher than RB. If this relation is okay with this graph,
Yes.
yeah. So only they ask about this thing.
Hmm. I think in some class I have also gone through this graph.
Yeah. अ, अजय घटक ऑप्टिक्स की बुक में बहुत सारे ग्राफ हैं इस तरीके के.
Yeah,
जैसे
but those are like
2 pi m plus 1.
very old.
Yes. Fabricated is the very first cavity, optical cavity.
Yes.
Okay. So which
Yeah,
of the
there was
cavity?
given
Sorry.
like delta omega is equal to 1 by tau cavity or something like that.
Delta omega.
Del- Equal to 1 by tau cavity.
No, delta omega is just equal to tau only, because omega upon delta omega is equal to q. Okay,
Okay.
and q is 1 by tau.
Okay. Okay.
So tau is, you can say something like that. Higher the delta omega, higher will be the tau,
Okay. Okay, sir.
and lesser the q factor. So which of the cavity A, B or C will have a longer lifetime?
So it will be inversely proportional.
Yes. So q factor RC हो जाएगा ना.
Yes, sir.
Tau will be higher. So I said tau C will be greater than tau B and tau A. Longer lifetime. Sorry, lifetime will also be 1 upon tau.
Tau is a lifetime, na?
Yeah, tau is the last name, then q is something proportional to tau. Sorry. The next is the phase shift mask. Technique used in nano fabrication change the phase of light in the adjacent pattern, leading to destructive interference. A graduate student wants to use a glass n is equal to 1.5 psm to obtain a phase shift of 180. For the wavelength 600 nanometer, the thickness of the mask required to obtain the required phase shift is thickness of mask. We have to calculate.
I think it will be something lambda by 2 or something like that for 180
Yes,
degree phase shift.
180 degree pi shift we need, then lambda naught by 2n. Okay,
2n, okay, okay.
so because 1 lambda equal to 2 pi, right,
Yes, sir.
in year, then what will be the in the mass, because mass has the refractive index this one, so the
Yeah, 3,
lambda
2,
in
200,
glass
I
will
think.
be
200.
600 by 3 into 1.5 is equal to 3, so 200 nanometer thick phase mass we need.
Hmm.
Question number 13 is A strong coupling between atoms and cavity is observed in plasmonic nanocavity. Okay, a strong coupling between atom and cavity plasmonic nanocavity. And as statement 2 is plasmonic nanocavity have extremely small mode volume with moderate Q factor. Okay. Then statement is both S1 and S2 are true and S2 is correct explanation of S1.
Statement one I think is correct, but I'm not sure about the statement two.
See, in plasmonic nanocavity mode volume is very low. That is true. Why?
Okay.
Because light cannot penetrate in the plasmonic structure. Okay.
Hmm.
So uh, the mode volume is only on the surface.
Okay. Yes. Yes.
Less.
But in that case, how the Q factor is calculated? Like
Sorry.
in those cases, how the Q factor is related to this mode volumes?
See, they are saying ki moderate Q factor. Q factor
Hmm.
is very moderate in the plasmonic cavity because there are many ohmic loss and all these losses are there. So due to these losses, the Q factor is limited in plasmonic cavity, but mode volume is very high. Sorry, very
Oh.
low. Okay. So Purcell factor, if you calculate Q by V,
Hmm.
okay. So if V will be less, then also Purcell factor will be high.
Yes.
Okay. So that's why this atom comes with the strong coupling with this plasmonic cavity due to this plasmonic mode volume. Okay, so these are the correct explanation of S1,
Okay.
and S1 is true and S2 is false. All these. So this is the only this S1 and S2 is true and S2 is explanation of S1. Any other question?
Uh, Sir, I have a simple question. Like in general, like in even in a two-level system, okay.
Mhm.
So until or unless I am giving any external input, like in a light, so in form of light source or something like that.
Uh-huh.
So the assumption is this, there is no atom is traveling, no particle is traveling from state one to state two, right?
Yes.
So just suppose I am not giving any external input and keeping the two level system in some kind of room temperature or something like that.
Mhm.
Okay. So in those cases, like will the atoms will or particles will travel from state one to state two? Is there any probability of such kind of transmission?
Such type of transition can happens at room temperature. You are asking, right?
Yeah.
In two level system. See, this is all depends on the energy gap between two level.
Okay.
Maybe some see some electron also have imbalance when to conduction when can jump due to your thermal distortion and mm, some fluctuation, like thermal fluctuation can happen in general, I can say.
Okay. And just another thing, like, just give me 1 second. Uh, I'm just copy pasting a question here. Just can you guide me like how to approach this type of question? Actually, in class, sir has not touched upon this topic.
The
So,
gas atom in cavity C are excited by the laser pulse of duration T is equal to 1 by omega r, where omega r
it's
is the Rabi
the Rabi
frequency.
frequency. Omega is the Rabi frequency.
Sorry?
This omega is in subscript. Okay, so this is Rabi
That I
frequency.
understand. Frequency. The lifetime of atom in excited state is 1 nanosecond. Choose the correct histogram depicting the temporal evolution of the atom in state 2 after the excitation pulse ends. Guess pulse duration is T is 1 upon omega r. T is greater than 1 upon omega r. Rabi frequency, okay, this is meter per second. Sorry, it's per second to second. Okay, time T is greater than, मतलब लॉन्गर टाइम के लिए फ्रिक्वेंसी से. Okay, frequency. The lifetime of atom in excited state is 1 nanosecond. And what is the omega r?
This capital omega,
हाँ.
the Rabi frequency.
So Rabi frequency will be 1 10 to power 9 per second.
Uh, okay.
So choose the correct histogram depicting the temporal evolution of atom. I am not able to answer just now for this question.
Okay, okay. Actually, Imani sir has not touched upon this topic, so that's why I am also unable to answer this question.
Uh, T is greater than 1 upon omega r, and lifetime in excited state is 1 upon, sorry, 1 nanosecond, means 1 nanosecond is corresponding to 10 to power 9 hertz. 10 to power 9 hertz means this is गीगा से नीचे मेगा से ऊपर क्या आता है. ओके, चूज द करेक्ट हिस्टोग्राम. सो हिस्टोग्राम कौन कौन से हैं, कुछ है क्या?
Can I share the screen? Like, think that.
Yes, you can share.
Give me 1 second. Yeah, this question number 4.
The gas atom in cavity C excited in the laser T is, so T is 1 nanosecond, right?
Yes, yes.
So after 1 nanosecond, the probability of all is in this one. बी वाला होना चाहिए, क्योंकि अगर हम राबी स्प्लिटिंग के ज़्यादा पल्स से अगर हम एक्साइट करेंगे, देन इट विल गो टू द स्ट्रॉन्ग कपलिंग, राइट, एंड इन स्ट्रॉन्ग कपलिंग इट विल ऑक्सीलेट,
Okay.
and you are seeing this, all these are damped one.
But C is not damping. One.
I will come on later on this
Okay,
question.
sir, fine. No problem.
Okay, stop. Any other question?
Sir, just like one more question I have, like for the fabrication purposes.
Okay.
So, like if I want to, is there any like any lecture or handbook like from where I just can readily know the fabrication process and how to, since look, I am working in a theoretical field. Okay,
Okay.
so I just want to understand like how the fabrication goes. Like if sometime in near future I want to fabricate my device or something like that. So is there any book that you can refer that could help me to understand it very
uh,
quickly?
See, in journal you can search on YouTube. Many fabrication process can, many fabrication technique you can also get. Actually, my fifth week lecture is not recorded, so I have to record also 2 hour lecture. If you will say, I will only on fabrication I can record that lecture.
Okay, sir. Okay, fine, fine.
2 hour lecture. Mostly, see, in fabrication, there are two types of fabrication. Like one, you will find soft lithography. Okay, one is just a lithography like
Hmm.
photolithography, e-beam lithography.
Hmm.
Then you will also find soft lithography or nano imprint lithography. It is also known as. One is colloidal lithography. Okay,
Hmm.
so there are lots of technique to fabricate. Just uh, according to your material, according to your resolution, according to your application, I will say, the you can adopt different techniques.
Okay.
So, like whatever this is, e-beam lithography and photolithography. Okay, all these required clean room facility. Okay,
Yes, sir.
so in clean room you have to process all these lithography and all these things. And like if I want to say soft lithography or imprint lithography, okay,
Hmm.
in that thing also one step is for your this lithography, this e-beam or photolithography. First step is that one only,
Okay.
and then they use some PDMS mask to make the replica, and then they imprint. But the advantage is, like if you make one structure from EBL, okay,
Hmm.
then you make 50 masks, more than 50 masks of that structure on PDMS, okay, and then each PDMS stamp can work as a 50 time you can stamp that structure with one PDMS. So from only once if you get the structure from EBL or photolithography, you can make 50 by 50 times your structure. So that is the
Okay.
advantage of soft lithography, and you did not need that. See, EBL has very costly instrument, right? So That is the advantage of that soft lithography. But that soft lithography is only limited to some materials which can be prepared as a sol gel process, or some polymers which can be dissolved in some liquid and spin coated. On these material you can imply that soft lithography only. Okay,
Oh,
so this is the difference between soft lithography and this photo and e-beam lithography. In general, just I will brief something. So uh, should I share the screen?
sir, actually, can we discuss this when you will teach us the lithography portion for 2 hours? Because uh, actually I don't have water stored in my room. So
Okay, 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 no problem. Okay, then I will maybe one lecture I will give you on this fabrication process.
okay,
You
sir.
just tell me your free time.
Uh,
Mostly I will free on Saturday or Sunday if you ready. Okay, and then I will share that screen. There share that link on fifth lecture as a
okay,
fifth lecture.
okay, sir. Sir, can we do it in for the next week? Next,
In the same time,
no, no. Just give me one
next
second.
week, whenever you are free, and
Yeah.
also just tell whatever if you have some link to the students which have joined this course.
Okay,
So
sir.
that will be maybe some special lecture I can take
Mm.
on fabrication process.
Sir, I think on 28th of September there is some holiday. So
20th of
September.
20th of is it Thursday
Yes, sir.
next week?
Yeah.
Yeah, yeah, that day I can give. Just recall me once.
So sir, how can I get connected with you?
My number you can note.
Okay, sir. Just give me one second. Yes, sir.
980
980
double eight
88
566
566
51.
51 980 88 566 51.
Okay.
Okay,
Uh,
sir.
okay, if you don't have any question, then we can stop today's talk.
Okay, sir. Okay.
Okay.
Thank you. Thank you, sir. Very much. Sir. Hello.
Yes.
I just have another query. This week also, there the lecture notes have not been uploaded. So
Okay,
on the
okay. For
8th.
seventh one, I will upload today only.
Okay, sir. Okay. Thank you.